Once more, hello again. We are deep in chapter 6 on recursion in SQL. This is the lecture Advanced SQL. Even if you're looking at this particular slide and even if you're listening to the upcoming minutes, and you may think that you are in the DB2 course, but well, please bear with me, this is still Advanced SQL. Only the next problem, the next use case that we are tackling with recursion in SQL tastes something like a DB2 topic, like an internal of relational database systems topic, like a topic on the internals of B+ trees. So everyone, welcome back over from the DB2 course. And all the people in the Advanced SQL course that have not heard about B+ trees, don't worry. We will sketch the necessary details here, and I think you should be able to appreciate what's happening here. Okay, so an entirely different example. No strings, no regular expressions, no graphs, no Sudoku boards, no arrays, but B+ trees. Okay. What we are trying to implement here in the next few minutes is a physical operator, an internal operator for query processing that is not implemented in PostgreSQL per se, but one operator that we could simulate or emulate using recursive SQL. All right. So that particular operator, the so-called lose index scan, okay, is very useful if you need to evaluate queries of this particular kind. So you're scanning the rows in some table T and you want to remove all the duplicates. So in column TDUP, we expect a fair number of duplicate values. We want to remove almost all of them and only keep the unique dt.dup values in table T and output these on to the application or to the user. Okay, so it's about duplicate removal. There is an operator called index scan already built in to PostgreSQL. What we are trying to emulate and simulate here is the so-called lose index scan. Let's briefly sketch what index scan and lose index scan are supposed to do. All right, so we are talking about a situation where the rows of T have been organized in a B+ tree, in an organized ordered index structure. So the rows of T are not only found in the heap file, in the file that stores all the contents of table T, but the rows, the contents of T, or at least some aspects of these rows, are found redundantly in a tree-shaped index data structure. And I've sketched this tree-shaped index data structure here on the left-hand side. It's a search tree index structure that we can enter, like any search tree, at the root node here. All right, if we follow the leftmost path, in such a search tree, and this search tree is organized by t.dup values. If we follow this search tree to the very left, and we always follow the leftmost pointers in the internal nodes of this particular search tree, then at one point we will hit this spot here, the value x1, which will be the minimum tdup value found in table T. So the search tree will help us locate the minimum tdup value in table T very efficiently. All right, so this is something that's easily done. How about all the other distinct values in the tdup column inside table T? Well, the B+ tree can help us to locate these too. We don't need the rest of the B+ tree data structure at this particular point. The B+ tree is organized in such a way that we can now scan from left to right at the leaf level of the B+ tree. We will just scan the leaf level of the B+ tree and encounter all the tdup values, in the table T in ascending order. Okay, so we are scanning from left to right here. We will see ever growing tdup values while we scan from left to right. The maximum tdup value will be found at the very end of this chain of leaf nodes here in the B+ tree. Okay, so while we perform the scanning, we encounter ascending t.dub values. This, of course, makes it quite easy to find the distinct t.dub values. While we scan, we just ignore values that we've already seen. Once we see a value that is indeed larger than anything that we've seen so far, output that particular value. Just scan, but do not output while we see duplicate t.dub values. Only output stuff like this value x2 or this value x3. This is meant to be unique values that we've not seen before. Only output these while we scan the B plus tree from left to right here. So that would be the normal regular index scan. That's also already implemented inside PostgreSQL. We could use the same B plus tree index structure, which of course is already present in PostgreSQL, to evaluate this select distinct query in a different fashion. And in this different version, in this alternative implementation, we would make better use of the fact that this is indeed a search tree that we can repeatedly search for particular t.dub values in the beginning. At the very first moment of our search, we would indeed, just in the case on the left here, we would indeed look for the minimum value that or t.dub value that we can find. And of course, this is easily being found by just following this leftmost path here until we hit the x1. So nothing has changed so far. All right. What we will do now is to use that x1 value, output it into the result, and then use it as a search criterion to re-enter the B plus tree at the top and look for any t.dub value that is strictly larger than x1. All right, so this is exactly what a search tree can do for us. We will enter the tree here. We will perform comparisons of the inner keys that have been stored inside the entity, the B plus tree, and that search will guide us through the tree down. Well, such a tree is not particularly deep, but it will lead us to this value x2, which is the next value strictly larger than x1. And we will immediately output this particular value. Don't be fooled by the fact that this path that we've just followed, that this path looks larger in our sketches here, or looks longer in our sketches than this particular path. Following this particular path involves more comparisons and more page accesses, more I/O operations. Following this path from x1 over to x2 will involve more I/O operations than following this path from the root down to the leaf level while we are searching for the value that is larger than x1. So a typical B plus tree has a depth of maybe 2 or 3 nodes. So that means 2 or 3 page accesses will suffice to find this value x2. All right. So x2 would be the next value that we output during our loose index scan. We would then use x2 as the next value, as the next criterion that we use while we search the tree from the root again. So we will look for the next value that is strictly larger than x2, and we will follow that path, and we will probably lead to x3, which we will output. x3 is the next value to start with at the root. We will perform our search and then probably not find any value that is larger than x3 in this particular example. All right. So that would mark the end of our search. As we will see, such a search will lead to a null value that we output, and that will help us to terminate the iterated search. Of course, the iteration is referring to our repeated use of the B plus tree to look for x1 and then for x2 and then for x3 and so forth. In the end, the result of the loose index scan and of the index scan will be exactly the same. But well, we have reached these results in well, quite different ways. Okay. The interesting observation is that we can implement this loose index scan. That's unfortunately not implemented in PostgreSQL using a recursive common table expression. This slide contains the entire implementation of the loose index scan. All right, so it's still a single slide implementation of the entire problem or use case. We will encounter larger code, larger SQL code in the upcoming examples, but hey, this still fits a single slide. All right, of course, we will again have the base case query and the repeated iterated query, and then there's some post-processing here. Okay, so the usual stuff that we expect to find. If you recall how the whole process starts, well, we were looking for this value x1, the minimum value of the TDUP column that we can find inside table T. And this is easily found. We would just use the min. We would just use the regular min aggregate that is already built into SQL. If you have watched the associated DB2 course videos already, then you will know that a B+ tree can perfectly well implement this min aggregate. It will just follow the very leftmost path inside the B+ tree to find this minimum value x1 in very few simple steps. So this search for the minimum TDUP value here indeed implements the traversal, or let's go over to the left hand side, we are doing loose index scan. This will indeed implement the traversal of this leftmost path here to find the value x1. All right. So what we will find in the loose table, this is a single column table, is the value, the last TDUP value, the smallest TDUP value that we have found so far. Of course, in the beginning it's the minimum TDUP value. So this would be the invariant, right? So this value, this xi value, will be the smallest value, TDUP value, that we have encountered during our processing so far. Okay, let's keep that in mind. When we now iterate over this, using this query, then we will look at what we have found so far. We will look at the smallest value that we have found so far. If that value is not a null value, well, if the T table is empty, then this min computation would already yield a null value. Okay, so then everything would be over already. So this would just yield a null value. We would not qualify against this predicate, and the iterated query would immediately yield 0 rows. So we would immediately terminate the recursion. But let's assume that we have found one minimum TDUP value, and it's found in this particular column. All right, well, then we would use this particular value as a search criterion in our B+ tree. So this type of predicate, such where predicates, so-called range predicates, are perfectly well implemented by B+ trees. So this will trigger a B+ tree search. We will enter the B+ tree at the root of the B+ tree and perform a search for the next TDUP value that is larger than the smallest value that we've seen so far. This is the expertise. B+ trees are perfectly well suited to support just this particular operation. All right. Well, we would the minimum value, the leftmost value that is still larger than the smallest value we have found so far, this would be our next output value. All right, so this would be our new xi value. All right, and of course it would be added to the accumulated result of our recursive common table expression, and would indeed be the next value that we use on the next iteration of this query to find the next larger TDUP value, and so on and so forth. Should there be no TDUP value that indeed can qualify against this comparison, if we have found the largest TDUP value already, well, then this minimum aggregate, as I told you already, will yield a null value. Okay, so on the next iteration, we will find a xi value that is indeed null. That value would not be able to qualify against this particular predicate, right? this would yield the empty table and the recursion would be terminated, just as we wished for. All right, and I think this is all there is to it. This is an implementation, a single page, a single query implementation of the lose index scan operator. Okay, will this effort be worth it? Well, if you look at some timings that you can perform using the SQL code that I will show you in a minute, and that I will also post to the repository, of course, as always, then you can indeed find some cool benefit there. Let's assume that our table T carries 1 million rows, okay, and that there is indeed the dub column inside table T that carries some duplicates. You see that I've performed a range of experiments here with a ranging number of duplicates. So only 10 duplicates, only 10 distinct values. I'm sorry, only 10 distinct values in the dub column. This means that the cardinality of the result of a select distinct query will only be 10. It will only contain 10 distinct values, or maybe 100, or maybe 1000. Well, it depends on the experiment that you're trying to perform here. Right, and then we would just perform timings. How long would it take to do a regular index scan? A regular index scan that scans the 1 million entries on the leaf level of the B+ tree on table T. That would be the number of milliseconds that you will see and record there. This would be the number of milliseconds that the lose index scan will need. And you can see if the number of duplicates is rather small, if it's in the range of tens or thousands maybe, then the lose index scan is vastly superior to the built-in index scan. So I think this is worth considering a bit. So this is the emulation on the user level of a physical operator, and it's still by a factor of 10 or maybe even 100 faster than the regular built-in index scan operation that has been coded in, of course, in terms of C inside the database kernel. I think this is quite remarkable. Of course, the savings stem from the fact that there is only few duplicates or distinct values to be found, and only few re-entries of the B+ tree at the root are needed. So this is testament to the efficiency of B+ trees, but it's also testament to the efficiency of the evaluation of recursive queries in SQL. All right. So if the number of root to leaf traverses in the B+ tree is not excessive, then the savings really can be substantial. I've performed these measurements on an idle MacBook Pro, which is just the MacBook Pro sitting here, which is just being busy doing the video recording. I can now switch over to the terminal and show you the experimental setup here. We can also perform the experiment, but we probably will see quite different timings, well, since the system is so busy currently. But let's see. Well, let's create table T here, the table that will also contain the dub column, which will carry all the duplicates. So let's create that table. There it is. Right, then let's populate that table. Let's create a table of 1 million rows. Okay, just like in the experiment on the slides. And in this setting, let's create a dub column that carries 1000 distinct values. Of course, it will carry 1 million values, one value in each row, but only 1000 distinct values. Okay, so we can easily change this later to modify the experiment. Okay, so this query will just populate the table. Okay, you can see that I'm using this modulo operator here to make sure that indeed only distinct vals, number of distinct values are being generated in the dub column. Okay, so generate and fill the table takes some time. All right, there it is. And now let's create the B+ tree. Let's create the B+ tree, that search tree index structure that will help us to navigate the values in the dub column. Building that index takes a few seconds, all right, and then analyze the situation so that the system takes its time to study the B plus tree, the value distribution in the columns and so on. This takes some seconds. All right, so let's already scroll down to the experiment here. So what you will see here is that I'm comparing the timings for two distant operations. I'm just performing the regular distinct operation on the TW column in table T. This will of course use the regular index scan built into PostgreSQL. Okay, very simple, very compact query. And then below here is our re-implementation, our emulation of the loose index scan. And this is just the code heavily commented. This is just the code that you've just seen on the slide, nothing else. Okay. So let's see how long such a duplicate elimination operation on table T will take if we just use the built-in index scan on the TW B plus tree. All right, so 1.5 seconds I see. Right, this is super slow also because of the video encoding here. Right, so now let's employ our loose index scan. You see, it's a much more complicated query. It will lead to a quite complicated plan. For those that are attending the DB2 course, you will appreciate how complex the plan is, but still it evaluates much faster. So 200 milliseconds as opposed to 1500 milliseconds. Have a look at the plan here. Those that attend the DB2 course will recognize some of the operators here. This is quite the plan. And it still performs so much faster than just the built-in index scan. Right, and I think the gap will even widen if we remove or if we reduce the number of distinct values, inside our T table. So let's throw the old T table contents away and generate new contents. Okay, 1 million rows. In the DUB column there are only 10 different distinct values to be found. The values 0 to 9. We don't have to recreate the B plus tree, it's automatically maintained. All right, so we've got a new table now, a new T table with only 10 distinct values in the DUB column. The normal index scan takes, well, 1.7 seconds in this particular case, and now the loose index scan. What? 9 milliseconds. All right. So the loose index scan is something that the PostgreSQL guys probably should consider at one point in time, it appears. But well, I think it's a really awesome. It's a different use case of using recursion inside a relational database system. All right. So much for that. Way more interesting, cool recursion stuff ahead. I hope you stick with us. And I'm looking forward to show all the neat stuff to you. Until then, take care and bye-bye.